Okay, you're going to see that a lot of these problems end up dealing with this formula G, the strength of the gravitational field equals gm over r squared. I would just memorize it. It comes from, like we did in the lesson part, Fg equals gm1 m2 over r squared. This becomes mg. We cross out one of the masses, and then this becomes the mass of the planet or the thing that we're placing the object in the gravitational field of that thing. So what do we have here? We have a planet that has 1/10 the mass of the Earth, and its diameter is 1/2 of the Earth, and the acceleration due to the gravity on this planet, planet X, is what? Well, let's take a look at what we've done. It's 1/10 the mass, it's 1/2 the diameter, so we can just put those changes into the formula. We square that half, and that gives us 4/10 g. G is 9.8, or in the AP they use 10, so that gives us 4 meters per second squared. Okay, in the next one, we have a satellite going around in an orbit like this, and the satellite goes from X over to Y, and what's true about its speed and angular momentum? Well, out here, it has a tremendous amount of speed because it doesn't have much potential energy. Out here it's moving slow, but it has a greater potential energy. So the speed increases when we go from X to Y and slows down from Y to X. And the angular momentum, there's no net external torque, so the angular momentum stays the same. So that's choice D. In this one, we have a planet. And again, we're going to be changing parts of these things in this planet. So that means we're going to be dealing with this formula again that comes up so much in these multiple choice problems. So what are we changing? We're saying that the mass is 4 times the mass of the Earth. The radius of the Earth is RE. They're just defining it that way. And they want to know the gravitational strength on the surface of this planet to that of the surface of the Earth if the radius of cosmos is equal to. And what is that going to be? Well, we are going to have to double r so that r squared becomes 4 to divide that by 4 to cancel out that effect. Think of it this way. 4 divided by what cancels out to produce that same gravitational field G? Well, 2 squared gives us 4. 4 divided by 4 is 1, and so therefore we need to double RE. Okay, in this problem we have 2 satellites. They're at 2 different radii. This is double the radii of this. And they want to know the ratio of the accelerations. So the mass of the individual satellites don't matter. They didn't give it to us anyway. It just depends on this mass. So we're going to use the formula G equals gm over r squared. What have we changed? We've doubled the radius. So therefore that becomes 1/4. So A2 is 1/4 of A1. In this question, we went over this in the lesson idea. The radius of the Earth is 6,000 kilometers. What's the acceleration of an astronaut in a perfectly circular orbit of 300 kilometers above the Earth? Well, 300 kilometers of the Earth is a very small fraction of the radius of the Earth, so it's very close to the surface of the Earth. So therefore, we can just, instead of doing a calculation, we just look at the choices here. We know it has to be less than 9.8, but only a little bit less than 9.8. So our answer is D. Okay, in this question it says a satellite moves in a stable circular orbit at speed v0 at a distance r from the planet. And for this satellite to move in a stable circular orbit at 2r from the center, the speed of the satellite must be what? Okay, so we're dealing with the centripetal force here. And the centripetal force, mv squared over r, is going to equal mg. So that gives us a formula for the acceleration due to gravity. That's equal to v squared over r. Well, we know that g, little g, is gm over r squared, so we can set that equal to v squared over r. Solving for v, that gives us radical gm over r. So that's going to be 1/2 on the inside, because G and M, you could think of this as a constant, so V naught we would say is 1, then the change would be due to the radical 2 on the bottom. Okay, this problem is basically just a trick. You have one planet, the Earth, pulling on a satellite, and the question is, what's the satellite pulling on the Earth? It's an equal and opposite force, so they must be equal. Okay, in this question we have a planet that has twice the mass, but the acceleration due to the gravity on the planet's surface is the same. So we have double the mass of the new planet, so we have G equals gm over r squared, so that's going to give us a 2 in the top, and we want it to have the same G, so if we put a radical 2 in there, that's going to be radical 2 squared, which will give us 2, and those will cancel out to give us the same G. In this one, we have a small mass released from a very great distance away from a large stationary mass. Which of the following graphs best represents the gravitational potential energy of the system as the two masses as a function of time? So we know that the potential energy must decrease and the kinetic energy must increase exponentially. And that's because the acceleration is increasing. The force is not constant. So therefore, we're going to have this increase into kinetic energy is going to be a curve. Now, it can't be this answer because look at what's happening to the slope. The slope is decreasing where we know that the slope has to be increasing. In this question, we have an object or a satellite going around a planet, and it gives us these two different radii, R1 and R2, and they want to know if the satellite has a speed of v1 at its closest distance, what's its speed at its furthest distance? Well, we know that the angular momentum here has to be equal to the angular momentum here because there's no net external torque. So what we can do is set these equal to each other. There's only one object, so the mass is the same, and crossing out those masses, we can solve for V2 in terms of R1, V1, and R2. So in this one, we have a circular orbit, and they're just saying the mass is m, the radius is r, and the velocity is v. So what must be true about this object in its circular orbit? Well, the first thing they said is its angular speed is v over r. Well, let's see if that's true. So we know that L is equal to I omega, and it's a point particle, so we can put in mvr, which is the same definition for tangential velocity. And by subbing in mr squared times omega for I is mr squared for a point particle, we end up crossing out some r's and we get omega is equal to VR. Now, we could also have done that straight from V equals R omega. It's the same idea. The tangential acceleration is 0. It is centripetally accelerating, but it is not tangentially accelerating, so this is true. And the magnitude of the centripetal acceleration is constant. That's because the centripetal force, the force of gravity, is constant in a circular orbit. In this next question, they give us a graph, and they say that the particle is released from rest with position r0. Its speed at position 2 r0 is most nearly what? Okay, so we have potential energy converted into kinetic. It goes from 3 to 1, so that change in kinetic energy is the change in potential, which is 2, and that turns into 1/2 mv squared. Isolate for v, and we get our answer. Okay, in this one, it says if the potential energy function is given by this formula, and B and C are constants, which is the expression for the force on the particle? So we have to remember that the negative derivative of potential energy is equal to the force. So what does that mean? Well, that means that we need to take the first derivative. So we take the first derivative of the formula that they gave us, and we get a formula for the force, which comes out as positive because that negative here cancels out the negative there. I have to admit that I got this question wrong the first time that I did it. The easier way to do this, well, I can first talk about the mistake that I made. The mistake that I made was that this distance right here, that's the distance that we use in F equals g m1 m2 over r squared. So we call that distance d. But then when we do the centripetal force, this distance right here is our radius. That's the point it's rotating around. So that's d over 2. So the easiest way to do this is just set the Fg equals gm1 m2 over r squared equal to Fc equals mv squared over r. And then that distance is d, and v squared over r, that's our AC, so that r is d over 2, and that gives us our answer with that 2 in there. So that's an easy one to make a mistake on. I also did this another way by starting out with AC equals v squared over r, and then working that into the G formula. Either way, you end up with the correct answer. And I just want to note that only 18% of people got this question right. So I think it really suckered people in to get this distance and this distance confused. Okay, this one deals with the Hohmann transfer orbit idea that we covered. And so we've got this satellite or spacecraft that's in a circular orbit, and it's at point P, and it gives a little burst of the ship's engine to increase its speed. That's going to push it into an elliptical orbit, which is this. And then the second part, and that's the answer, you're done right there. But the second part, to put it into a Hohmann transfer orbit, would be to give it a second burst to make it go in a circle. So this is half of the Hohmann transfer question. Okay, this one is kind of tricky. They give us this graph, and it's the force on a planet or whatever they ask you, the Earth, radius r. And we know inside it decreases, outside it also decreases. And they want to know the work done by the force of gravity when the small mass approaches the Earth from far away and is placed into a circular orbit of radius r2. So it's going to be moving from here to here. So we can look at this as starting out as infinity, and then we are moving it to r2, which is our new r. So what is that new r? Well, that's the work is equal to the integral of f dx, and that's equal to u. So then we say that this goes from infinity to our new r2, which we're going to define as r. And then lastly, we have an escape velocity problem, and we went through that in detail. I'll just briefly go over it. For escape velocity, we start out with our initial energy, and we end with our final energy. At infinity, when it gets to infinity, we're defining our potential energy as 0, and our kinetic energy, it has to stop and not come back, so that is also 0. So our potential energy is actually negative on the surface, so we just set the negative potential energy plus the kinetic energy with the escape velocity on our initial side, and then that's going to add up to 0 at infinity. Add this to the other side, and divide for our escape velocity formula. If you memorize this, then you could have shortcutted this. And they want to know how it would change. And we would double the mass of the Earth to get us that radical 2 VE.